Hi everyone, welcome to Deep Learning Talks. So today we are going to talk about bidirectional encoder representation of transformers, which is BERT. So we've already seen decoder only transformers. So we've already seen encoder decoder transformer, which is in the case of attention is all you need. Now there is another dimension of transformer, which is encoder only transformer. So we've seen two jargon keywords, encoder, decoder. We'll see how they differ. And in case of the first architecture which we saw in attention is all you need, we had encoder decoder stack. In the second architecture, where we talked about the GPT family, we saw the decoder only stack, which is the generative, the auto-regressive generation transformers, which is decoder means generative, right? Now we have another stack, which is encoder only. We'll correlate encoder only transformer with generating representation. So BERT does not generate text. BERT does not generate tokens in an auto-regressive way, in a sequence. It does not let you autocomplete. It does not let you write a sentence. It does not continue your story. It does not help you do a conversational chatbot based conversation with an AI, right? So it helps you produce rich, expressive, deeper contextual representation or embeddings. So what does BERT do? I think that's more or less now clear. And what does GPT do? GPT helps you predict the next token. If we were to figure out or look at the probability function for both of them, if so both of them are trying to do some maximum likelihood estimation, but let's see what GPT does, and we will see what BERT does with respect to probability at the end of the video. So GPT basically says what is the probability of token xt given all the tokens from x0, x1, x2, x3s, so on till xt minus 1, right? But BERT says something else, which we'll see at the end, obviously. Now, what happens in BERT? So since it's a transformer, we will have to prepare the input. The input is coming, let's say, from the whole lot of text on the internet, or the whole internet is represented as text, as a simple text file. Now, text is nothing but words. Words or sentences, and they are nothing but the statistical unit which we call as tokens. We see everything as tokens. To every token will have a token ID. Using a tokenization algorithm will run on all the tokens to produce token IDs. Token IDs is going to be discrete. They are not going to be continuous. Every token will have a token ID and token embedding. What do I mean by token embedding? Token embedding is a richer vector representation of each token in d-dimensional space. For example, if Puru is a token, Puru can be represented in a 512 dimension universe as a single data point. So I will need 512 elements stacked in a column, right, to represent Puru. Similarly, if I have 1 million such tokens, I will need 512 million sized array to represent my 1 million vocabulary. If I have context length L and my dimension D, I will need L cross D sized array to represent the token embeddings. Similarly, another L cross D size array to represent positions of all my tokens. So token embeddings correlate to meaning. Token embeddings express the meaning of a token. Position embeddings express the relative position of the token. Token embeddings are trainable. We know that for every transformer. Positional embeddings can be trainable, can be not trainable. We can use a static sinusoidal waves to generate positional embeddings. We can train them, right? The GPT family uses trainable positional embeddings, right? So token embeddings are always trainable, right? Now this input, since we have prepared the input, this input is going to go to the multi-headed attention block or the attention block or the attention sublayer. The attention sublayer is going to produce one head. One head is nothing but an attention matrix, the contextual representation between every token, every pair of token I comma j, right? It's going to produce an n square matrix where n is the length of the token, right? Number of tokens. So number of tokens at that particular instance will produce an n square matrix. One head is going to produce one matrix, but now we don't stop at one head. Multi-head attention block says that why don't we have multiple heads? Multiple heads means you will be able to capture deeper and hierarchical relationship. So deeper hierarchical relationship is the crux of deep learning. Why? Because in case of neural networks, we saw that we can have multiple hidden layers. Multiple hidden layers means better feature extraction, better understanding of the modality that we are dealing with. Or in case of convolutional neural network and deep computer vision, we saw that we need more and more convolution blocks. We don't stop at VGG16, we go to VGG19. We don't stop at VGG19, we even go to a 50 layer neural network, 50 layer CNN, right? So deeper hierarchical representation is the crux of deep learning. Now, the multi-head attention block, since it produces attention, it does not produce attention the way GPT does. It does not have causal masking. What does causal masking mean? It does not hide, mask. So I can use masking and hiding, or deadifying, or nullifying the neurons, in an interchangeable way. So it does not mask the future token. Cat sat on mat. When I'm computing attention for on, I can see cat, I can see sat, I can see on, I can also see mat, right? If I'm talking about BERT, we don't do causal masking here. The embeddings that BERT produces are not causal embeddings, right? What we essentially do here is MLM. It's not multi-level marketing, it's masked language modeling. What does that mean? Masked language modeling basically means you mask or randomly nullify a couple of tokens randomly. It's like fill in the blanks. Cat sat on mat, I just masked mat, right? So that I can enforce the capability of fill in the blanks in BERT. BERT can predict the token mat, right? BERT can find out the maximum likelihood estimation for the missing masked token given the unmasked tokens. So this is how the probability function goes. What is the probability of x, x of t given the surrounding context, right? So BERT can see left to right, BERT can see right to left. That means BERT is bidirectional. BERT can see the past, it can see the future. That means it is bidirectional, right? In case of GPT, we only saw left to right and it was unidirectional. BERT is not generative in nature, right? So now multi-head attention is computed using masked language modeling. Then we have our traditional sublayer, which is add and layer normalization, add residual and layer normalization. That is very simple, and it goes as as it happens in GPT, as it happens in the attention is all you need based transform, which is the encoder decoder architecture. Then we have the feed forward neural network. So now feed forward neural network will fuse in a lot of non-linearity at every token level, and it will not produce softmax probabilities. It will only make the representations that we have produced richer and deeper and more expressive, but it will not produce softmax based probabilities. We don't have an output head. Because why it won't produce? Because we are not generating anything. We are not sampling the probability of a token from all the given softmax probabilities. If we were to sample the next token, if we were to predict the next token, then only we would need softmax probabilities. Here we have simple two linear layers and GLU activation. Along with that, we have add residual and layer normalization, and then we simply produce the output. So this is the whole architecture of BERT, and the major difference that we talked about is masked language modeling, then the directionality, and then the output. The output is bidirectional, and the output is a representation. It is not a predictive token. We don't use BERT for generating the next token. BERT was produced by Google, and all the great papers have come out of Google. So Google has a great research pedigree, but BERT changed the game a lot. The use cases for BERT are not autocomplete, are not code generation, are not sentence continuation. They are rather maybe infused in search or producing semantic similarity. If you can produce a vector representation, for a document, and you want to match it, let's say you are building a plagiarism checker, or you are building a document checker, you want to match or find out the cosine similarity or the similarity between the embeddings produced by BERT for document 1 and document 2, right? So BERT has these kind of use cases, not the traditional generative use cases. So I will just close by saying that the embeddings that are produced by BERT are not causal embeddings, they are masked language modeling based embeddings. The GPT based embeddings are built in such a way, are generated in such a way that all of those embeddings are referenced or are built on the basis of past tokens, right? Every token I embedding is based on the context of I till I minus 1, but BERT is bidirectional. So BERT has surrounding context, right? So BERT has masked language modeling based embeddings. So GPT also produces embeddings, BERT also produces embeddings, obviously in hindsight, but both the embeddings are also a little different. So along with that, there's one more point that I would like to mention, that BERT also is trying to maximize the likelihood of a token. GPT is also trying to maximize the likelihood of a token. GPT says that I want to predict the maximum likelihood estimation of the next token, but BERT says I want to predict, or I want to maximize the likelihood of this particular randomly masked token given all the unmasked tokens. GPT says given all the past context, BERT says given all the surrounding context. It can be left to right and it can be right to left. So these are some of the common differences, and obviously the use cases are traditionally or drastically different, and both of them are super relevant transformers. One is encoder only, which is BERT, and GPT is decoder only. The whole GPT family is decoder only. I hope this video was helpful. Thank you, and I will talk more about BERT in the next video.